Okay, so what we've looked at thus far is we've studied this diagram, and we've basically seen how friction is developed. It's only developed when you have the applied force, okay? And we saw that when the applied force is applied, okay, two things happen. Friction force develops and the normal force shifts to the right. Why does it do that? The normal force shifts to the right to counteract the moment caused by the applied force. We also saw that essentially for equilibrium, that's essentially what I said now, two things happen. As we apply the force P, two things can happen. The block can slip or the block can tip. In order to counteract slipping, we've got a frictional force that opposes that applied force. And in order to counteract tipping, we've got this normal force that keeps moving to counteract the increasing moment. That normal force causes a moment about that point, and it essentially is counteracting. But we will look at that, counteracting the applied moment, but we will look at that more in some problems. The next thing, so regarding slipping, okay? Regarding slipping, which just mentioned, let's ignore the tipping part for now. Regarding slipping, we need to look at something called impending motion. Okay? So just consider in your experience, if you've got the block there and the force is 0, you're not applying any force which wants to cause relative motion between the block and the surface. Then obviously the block will just stay there, and actually your frictional force is 0. That's what we've learned. But as you apply your force P, suddenly we have this frictional force that develops. And if you check your experience, take anything, take a table or take any object, you keep increasing P. You apply P, you keep increasing it, and the object is not moving. Then there will come a point where it will suddenly break free and begin to move, okay? So based on that, really we need to understand this diagram. On the horizontal axis, we've got our applied force P. On our vertical axis, we've got our frictional force F, okay? And based on what I just described, when your applied force P is 0, your frictional force is also 0. There's no frictional force. As you increase P, as you increase the applied force, the frictional force also increases. You keep increasing it, but it's not moving, okay? You keep increasing P, the frictional force keeps increasing. That opposing force there, that opposing force keeps increasing, right? Keeps increasing. As you increase P, you keep increasing it. And then there's a point, okay, where this box is on the verge, okay? I'll specifically use this, on the verge of slipping or sliding. It's also called impending motion. The point is, if you increase the force a little bit more, this box will break free and begin to move. This whole region, the box or the object or whatever it is static, stationary. I always get confused between the stationary that you buy in CNA and the stationary. Okay, I'm pretty sure that's how you spell it. Spelling is important, okay. So if I'm wrong, correct me, okay? At this whole stage, guys, this is very important. The box is not moving, okay? Then it gets to this point called impending motion or verge of slipping. And if you increase the force a little bit more, that box will begin to move. And what you'll find with the curve, it'll look something like this. As I continue to increase P, the frictional force drops, okay? And it stays constant while it begins to move. Now, what's very important is that at this point of impending motion, on the verge of slipping, okay? Verge of sliding. It's about to slide, about to slip. Your frictional force is given by this equation. Fs equals mu Sn. and I want to emphasize this very strongly, this equation is only valid at this point. You cannot use this equation over anywhere else along this curve. You can only use the Fs equals mu Sn equation at the verge of slipping, at impending motion. That is the only time you can use that equation, okay? Then as it begins to move, then we've got another equation, okay? Fs is mu Kn. Okay, so that is your kinetic friction. By the way, this is called your limiting static friction. Okay, limiting static friction. Limiting, okay, because it's at the limit. Okay, and static because it's not moving. So this frictional force keeps opposing the applied force, up until a point. That maximum point is given by this. You can only use this at that maximum point. Then the box breaks free, begins to slide, and at this point we can use Fs equals mu Kn. Mu S is your static friction coefficient. Mu K is your kinetic friction coefficient. All right, so it's very important when we are in this range here, and we are not on the verge of slipping or at impending motion. If we want to solve for F, right, we have to just simply use our equilibrium equations. P minus F equals 0. Okay? If we're at that point, then we can use our equilibrium equations plus Fs equals mu Sn. Please take note of this. When we are not at the verge of slipping, okay, let's write this down. Let's make it kind of official. When we are not at impending motion. Not at impending motion. Then we can just use our equilibrium equations to solve for any unknowns, solve unknowns. All right? What are those? Those are sum of the forces in the x is 0, sum of the forces in the y is 0, and sum of the moments about some point is 0. All right? So when we are not at impending motion, the frictional force is just an unknown. It's an unknown force just like any other force that we are trying to solve for, and we would solve it using these equations. Okay? Just like, so you've got your object, you've got an applied force, you've got weight, you've got F. F there is just simply an unknown force. The object is in equilibrium, so we can try to solve for F using our equilibrium equations. If we know we're at impending motion, then if at impending motion, then we can use equilibrium equations plus limiting static frictional equation, plus that. So we can use all our equilibrium equations plus this, because we know we are at that point there. Okay? So I hope that's helped. Hope that's given you a bit of a background. So when you're solving your problems, you need to find out, are we at impending motion or not? If we're not at impending motion, I can only use these equilibrium equations to solve for any unknown forces. If we are at impending motion, then we can apply these plus this guy, which only is applicable at impending motion. Okay? Cheers. I think that's good. Cheers.